All right, guys, today we're looking at 8.3 Laws of Logarithms. And if you turn your attention to this part first, I'd like you to take out your calculator and compare log 30, or log 5 times 6, and then secondly, log 5, and we want to get an answer, and then times it by log 6. And then down here, same thing, log 5, hit enter on your calculator, and then add log 6 and see what you get. So this might be a good point to pause the video and calculate those. And what you should see is that comes out to be 1.477. If we round it, 0.544. And down here, 1.47, oops, there we are, 77. So the product law of logarithms is illustrated in this example that the log base c of m times n can be written as log c m plus log base c of n. And this is on your formula sheet. There's no need to memorize that guy, but there it is. And so this is kind of similar to the exponent law, in which when I multiply two powers, I add the exponents. So similarly with a logarithm, when I multiply m times n, I can represent it as the sum of these two logs. All right, next up, we have the quotient of logarithms. And maybe I'll just do these calculations for you to save some time. This turns out to be 1.079. This is 3.2618. And down here, also 1.079. So we can see that when I'm dividing two logs, when I'm dividing m by n for this log, base c, that I can represent it as two separate logs, log base c of m minus log base c of n. So again, similar to our exponent law, in which when we divide two powers, we subtract the exponents. And remember, I've been saying that a logarithm is an exponent. So there we subtract them. And then down here, the power law of logarithms. I've got log base 125, log base 10 of 125, or log of 5 cubed. And both of these turn out to be 2.096. And then down here, in this other one, where I've got 3 times log 5, I end up with the same, 2.096. So in general, if we turn our attention back to this side, what I'm doing is taking that exponent and dropping it down in front to become the coefficient. So this is p times log base c of m. And you can see over here, I took that 5 and plopped it down in front to get, that 3 and plopped it down in front to get 3 log 5. Okay, and now with this one, I've got log cube root of 8, which turns out to be 0.301, or log of 8 to the power 1/3. And we know from grade 10 that these mean the same thing. And so down here, when I've got 1/3 times log 8, I've really taken this exponent and plopped it down there in front, just like I did up here to get 3 log 5. So if I do this on my calculator, I see the same thing. It's 0.301. And so over here, I can rewrite log base c, the p root of m, as log base c m to the power 1 over p. And then again, I'm going to bring this exponent down in front. So I have 1 over p log base c of n. And so these are the 3 laws of logarithms that we're going to practice today. And again, all 3 of them are on your formula sheet. So next, we've got a couple of examples, and we're going to rewrite them by separating them out into individual logs of x, y, and z. So here the base is 6. I've got x over yz. So I'm going to separate this as log base 6 of x minus log, again, base 6, that doesn't change, of y minus log base 6 of z. And so another way to think about this is in this expression up here, the power on x is positive 1. So there's like an invisible 1 here. And on the y, if we remember, if that's in the denominator, its power is really negative 1. And so there's a negative 1 in front of that. And same thing here. So that's another way to help us think about that. Okay. Then next, this guy, log base 5 of root xy. I would write log base 5 xy to the power 1/2. Although the index isn't written here, we know that it's a 2. And now I'm going to write this 1/2 in front. Log base 5 x y. And now I can separate these 2 logarithms using the product law. So I would have 1/2 log base 5 of x plus log base 5 of y. And over here I've got 2 examples for you guys to try. So why don't you take 2 minutes and try those. All right. So if I separate this out into 2 logs, let me draw a line here. I've got log base 3 of 9 minus log base 3 of the cube root of x squared. So looking at this part here first, log base 3 of 9, this is really saying what exponent on that 3 will result in 9. And the answer to that is 2. So we can really just write that as 2. And here, minus log base 3, I would rewrite this in exponential form. So the 3, that's the index here, becomes the denominator of the fraction, and the 2 that's over here becomes the numerator. So I've got 2 minus log base 3 x to the 2/3, and I'm going to drop that 2/3 in front like this. So there's that guy. And the last one, if we separate that out, I would maybe write log base 7 of x to the 5th y minus, because this guy's in the denominator, log root z. And then I might give myself some more room over here to work. And I would separate this first logarithm into log base 7 of x to the 5th plus log base 7 of y minus log, and instead of rewriting root z, I might write z to the power 1/2. And then in the last step, I'm going to apply the power law of logarithms and drop this in front, as well as here, that 1/2. So I have 5 log base 7 of x plus log base 7 of y minus 1/2 log, oops, I forgot the base 7 up here. Sorry about that. There it is. And 7 of z. So what this is really saying is that x and y are positive. They're in the numerator up here. The power on the x is 5. And because this is a negative 1/2, that means The log base 7 of z is in the denominator, it's negative, and it's a square root, so I have the 1/2. All right. So here we're going to use those logarithm laws to evaluate, so come up with what this actually equals. So let's start with maybe A and C, and then you can pause the video and you can try B and D. So in part A, what I might do to start is separate the 9 and root 27, log base 3 of 9 plus log base 3 of root 27. And then I might remember that root 27 over here, if I get rid of that root and I write it as a power 1/2, in my next step, I can plot that 1/2 here in front. So I've got log base 3 of 9 plus 1/2 log base 3 of 27. And then if we think back to what we know about logarithms, in this first one, 3 to what power equals 9? What is the exponent in this case? Well, it's 2. We saw that already in this lesson. Plus 1/2 times 3, and again, to what power is 27? Well, that's 3. So I'm adding 2 and 1/2 times 3. So I'm adding 2 and 3/2. So that's going to be 3 1/2. And coming over here to look at part C, I can just evaluate this logarithm right here and this one, and just leave the coefficients where they are in this particular example. So I have 1/2 times log base 2 of 64. So again, 2 to what power is 64? And that is 6. And here, 1/3 log base 2 of 8, 2 to the power 3 is 8. Remember, the logarithm is the exponent. So 1/2 times 6 is 3. Half of 6 is 3. And 1/3 times 3, well, that's just 1. And 3 minus 1 is 2. So the value of this whole expression up here is 2. So why don't you try B and D? Okay, in B, what I might do is rewrite it log 5, 1,000 divided by, because I'm subtracting these two, 4 times 2. And so I would end up with log base 5 of 125. And this is just 3. Remember, 5 to the power 3 gives me 125. Part D, I might first apply the exponents that I have in front, the 2 and the 1/2. So I might pop that up there and get log 3 of 36 minus log 3. 64 to the power 1/2 means the root of 64, so that's 8, plus log base 3 of 2. And now, at this point, I might combine all 3 of these into a single logarithm, log base 3, 36. I'm going to have to divide by 8 because I'm subtracting it here. So 8 goes in the denominator, and the 2 that you see at the end over here is going to be in the numerator because I'm adding it, so times 2. All right, so we've got log base 3. 36 times 2 is 72 divided by 8. And there we go. Log base 3, 72 divided by 8, that's really 9. So 3 to what power is 9? Well, we know that that's 2. So the value of this whole ugly expression up here turns out to be 2. All right, in the next example, we're saying that x is equal to a particular logarithm, log base 3 of 5, and y is equal to log base 3 of 2. So what I want to do here is express 40 as 5 to some power times 2 to some power. So you might remember that 40 is 5 times 8. So I might write this as 5 times 8. Well, that's 2 cubed. And now I'm going to apply my law of logarithms to separate this into log base 3 of 5 plus log base 3 of 2 cubed. And this, you can see, is the same as that. So the first part is really just x. And here, this is almost y, except I have this exponent that I don't have over here. So I'm going to have to drop that down in front and get plus 3y. So in this case, if log base 3 of 5 is x and log base 3 of 2 is y, then the log base 3 of 40 would be x plus 3y. So what you might want to do now is pause the video and try this one. All right. Again, here I'm going to separate this as log base 3. 25 is 5 squared. And I'm going to subtract that 2 because it's in the denominator. So log base 3 of 2. This is really just y. And here, in the first term, I'm going to pop that 2 down there and get 2x. So this is really 2x minus y. In example 4, I'm going to apply the law of logarithms again and rewrite this as a single logarithm. So I'm doing kind of the opposite of the first part where we were expanding it. Now it's expanded, and we're going to put it all together. So what I might do first is add these. I have 4 log base 3 of x minus 1/2. Here I've got a log base 3 of x and 5 of the same. So that's really 6 log base 3 of x. I'm just adding this 1 and that 5 to get 6. And now what I might do is multiply the half times 6 to get 3. So I have 4 log 3x minus 3 log 3 of x. And now, what am I going to do? I'm going to pop this exponent up here and up there. Oops. And get log base 3 of x to the 4th minus log base 3 of x cubed. And then apply the quotient law. So I have log base 3 of x to the 4th over x cubed. And if I simplify that, it's just log base 3 of x. And another way you could do that at this point up here is just subtract 4 minus 3. Well, that's just 1 log base 3 of x, and we would get there directly without those 2 additional steps. So maybe take a minute and try this one. Put that all together into log, in this case base 10, remember if it's not written, it's base 10, of some powers of a, b, d, and e. All right, what I might do now is combine these. Log b times d. I might pop that exponent up, and this exponent up as well, and I would get minus log e to the 5th minus log a squared plus log a to the 1/2. And now if I put this all together, b and d will be in the numerator along with a to the 1/2, because that's a positive logarithm there. And these two are going to end up in the denominator because they're negative. I can think of that telling me that this -5, the power on the e is really -5. So it's going to end up in the denominator, e to the 5th, and here a squared. And then lastly, what I would notice in here is that I've got a's in the numerator and the denominator. So I'm just going to simplify that. Log b times d. A is now gone. In the denominator, e to the 5th. And down here, I'm going to end up with 3/2. If I take away from this half, that 1/2, I end up with 3/2 for the power on the a in the denominator. All right. In example 5, we have a science example, the pH scale, which is a logarithmic scale. There are a handful of these that you'll see in the assignment. pH is one of them. There's decibels is another logarithmic scale. The Richter scale for earthquake intensity is also a logarithmic scale. And so here's a little explanation of it. 7 being neutral. Anything lower than 7 is an acid, and down here a base or an alkaline substance. So the question is, or says that black coffee has a pH of 5.1 and the pH of milk is 6.6. How many times more acidic is the coffee than the milk? So what we need to do here is apply the pH formula, which is pH is the negative log of x, where x is the concentration of hydrogen ion. And so what we want to find is what is that x for coffee with a pH of 5.1 and then the milk with 6.6 and compare those two to see how different they are. So if I think about coffee, its pH is 5.1. That's this side of the equation, equals the negative log of x. So to find x, what I might do first is move that minus sign to the other side by dividing by -1. And now I would just exchange this logarithmic form for the exponential. So I know that the base is 10 when it's not written. So the value of x is 10 to the -5.1. And that's for coffee. Yeah, that's the coffee. And if I do the same calculation for the milk, I'd have 6.6 is the negative log of x. Again, pop the negative over to this side. And convert it from logarithmic to exponential. So base 10, the log equals the exponent, and that gives me the value of x, in this case, for milk. And now lastly, what I would do is divide these. And so the trick is understanding that 10 to the -5.1 is a bigger number than 10 to the 6.6. So all I'm going to do is divide those. 10 to the -5.1 divided by 10 to the -6.6. And that's going to give me the number of times more acidic this the black coffee is compared to the milk. And so if I put that in my calculator using the button for scientific notation, the E button, capital E, you see that's above the 7 on the Texas Instruments calculator. So you have to hit second function, and then you get that capital E, which means times 10 to the. So I could put in, oh, actually, ignore that, scrap that. This is already 10 to a power. So I'm just going to use 10 to the -5.1 divided by 10 to the -6.6. Sorry about that. And what does it come out to be? 31.6 times more acidic. So there's an example for pH for you.